Tonight, we're going to talk about one of the strangest paradoxes in modern science. The nearest star to our Sun, Proxima Centauri, sits just 4.24 light-years from Earth, and on August 24th, 2016, astronomers at the European Southern Observatory confirmed that a roughly Earth-mass planet orbits in its habitable zone, a rocky world, close enough that its light reaches us in a little over 4 years. By every measure of cosmic distance, it is right next door, and yet no human being will ever stand on it. Not in our lifetimes, not in our grandchildren's lifetimes, not on any timeline current engineering can describe. The physics permits the crossing, the engineering does not. By the end of tonight, you're going to understand why 4.24 light-years is both impossibly close and impossibly far, how Proxima Centauri b sits inside a habitable zone we can see but cannot reach, and what the gap between theoretical possibility and practical accessibility tells us about the true shape of human reach into the galaxy. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The announcement came on August 24th, 2016. The European Southern Observatory released a finding that traveled through the scientific community like a current. A planet had been detected orbiting Proxima Centauri, roughly Earth mass, rocky, sitting inside the habitable zone, the band of orbital distance where temperatures could, in theory, allow liquid water to pool on a surface. They named it Proxima Centauri b. For a moment, something shifted in how people thought about the sky. The nearest star to our Sun now had a world, not a gas giant, not a distant giant of ice, a world with a surface, a world with mass and rock, and a place in the zone where life, as we know it, could conceivably begin. And it was right there, 4.24 light-years away. The light leaving Proxima b's surface reaches Earth in a little over 4 years and 3 months. On cosmic scales, that is nothing. That is a neighbor. That is, in the language astronomers use almost apologetically, next door. There is something deeply human in the way that combination landed. A name, a location, a measurement you can hold. Proxima Centauri b is not a vague possibility somewhere in a distant arm of the galaxy. It is a specific place. You can point to it. You can write its orbital period in a notebook. You can calculate the temperature range its surface might experience. It has coordinates. It has mass. It has a year. For the first time in human history, the nearest potentially habitable world was not a category. It was a place. But here is where it gets strange. There is a difference between a destination you can name and a destination you can reach. We have been very good, for a very long time, at naming things we cannot touch. Proxima Centauri b is the most dramatic example of that gap we have ever found. The fact that we can describe it so precisely does not bring it any closer. And the precision, as we will see, is part of what makes the distance feel so specific, so immovable, so real. We will return to that gap. It is the subject of the everything that follows. But first, the place itself. Proxima Centauri is a red dwarf. Red dwarfs are the smallest, dimmest, and most common type of star in the Milky Way. Proxima has about 12% of the Sun's mass, and roughly 14% of the Sun's diameter. Think of the Sun as an average-sized beach ball. Proxima, on that scale, is barely larger than a golf ball. It produces only about 0.0016 times the energy our Sun does. That is roughly 1/600th of the Sun's luminosity. Proxima Centauri is the closest star to our solar system, and yet it is completely invisible to the naked eye. You cannot see it without a telescope. It puts out so little light that even at a distance of 4.24 light years, it does not register as a star you could find by looking up. Robert Innes found it in 1915 at the Union Observatory in Johannesburg, South Africa. He was conducting a systematic photographic survey of the southern sky, comparing star positions across different photographic plates to detect movement. Proxima moved. It moved in a way that matched the proper motion of the Alpha Centauri system, the bright pair of stars 4.37 light years from Earth. That matching motion suggested a connection. But for decades, astronomers debated whether Proxima was truly gravitationally bound to those companions or merely passing through the same region of space on an unrelated path. The question took time to settle. The binding has since been confirmed. Because Proxima is not alone. The Alpha Centauri system is a triple. 3 stars held together by gravity, moving through the galaxy as a group. 2 of them, Alpha Centauri A and Alpha Centauri B, form a close binary pair at the system's heart. Alpha Centauri, it is a yellow star, a G-type main sequence star like our Sun, but slightly larger, about 10% more massive and roughly 50% more luminous. Alpha Centauri B is an orange K-type star, smaller and cooler than the Sun, a little dimmer, but still a genuine star putting out real light. These two orbit each other in an elongated path that brings them as close as 11 astronomical units and carries them as far apart as 36 astronomical units. An astronomical unit is the average distance from Earth to the Sun, about 93 million miles. At closest approach, A and B are roughly the distance from our Sun to Saturn. At their farthest, they are separated by a gap wider than the distance from the Sun to Neptune. They complete one full orbit around each other every 79.9 years. Now, Proxima. Proxima Centauri orbits A and B, but not closely, not even remotely closely. Proxima sits roughly 13,000 astronomical units from the AB binary. 13,000. Our entire solar system, measured from the Sun out to the orbit of Neptune, spans about 30 astronomical units. Proxima's distance from its companions is more than 400 times the full width of our planetary system. It takes Proxima more than 500,000 years to complete one orbit around A and B. In the entire recorded history of human civilization, roughly 5,000 years, Proxima has traveled about 1% of one orbit around its stellar companions. That is the quiet reveal this system offers before we even begin to discuss travel. Even inside Proxima's own stellar family, the distances are vast. The Alpha Centauri triple is not 3 stars packed together in some tight cluster. It is 3 stars scattered across a gulf that dwarfs anything in our solar neighborhood. Proxima is a member of a system, but it is a deeply isolated member, a small dim ember orbiting at a remove that would take light roughly 78 days to cross. It sits slightly closer to us than A and B, which is how it earned the name Proxima, the nearest, the closest individual star to our Sun, a title that is real, a title that means something, and that small dim world in its habitable zone, Proxima Centauri B, is what we have spent 7 years looking at more carefully. Because the more carefully we look, the more complicated the word habitable becomes. What the surface of that planet actually experiences, what Proxima puts it through every day it exists, is something the Discovery announcement in 2016 did not fully describe. And that part of the story was still coming. So how do we even know it is there? That is the question the 2016 announcement answered, quietly, in its footnotes. There is no image of Proxima B, no photograph, no direct observation of a disk or a shadow or a silhouette crossing its star. What the astronomers at the European Southern Observatory detected was something far more subtle. They detected a wobble. Here is what that means. When a planet orbits a star, the planet does not simply circle a stationary object. Both bodies respond to each other's gravity. The star moves too. Not much, but measurably. It traces a tiny back and forth motion, a rocking, as the planet pulls it first one way and then the other. That rocking shifts the light the star sends toward us. When the star rocks toward Earth, its light compresses slightly toward the blue end of the spectrum. When it rocks away, the light stretches slightly toward the red. The shift is small enough to be almost nothing, but it follows a pattern, a rhythm, a repeating period that matches the orbit of whatever is pulling the star back and forth. This technique is called Doppler spectroscopy, or radial velocity detection. Think of it like the pitch of an ambulance siren. As the ambulance moves toward you, the sound waves compress and the pitch rises. As it moves away, the waves stretch and the pitch drops. The star's light does the same thing. And if you watch long enough, you can read the period of those shifts the way you would read a heartbeat. ESO astronomers watched Proxima Centauri for years. They were patient and methodical, and they found it. A periodic signal repeating every 11.2 Earth days. A rhythm locked into the star's motion. Something was pulling it. Something with a minimum mass of roughly 1.07 times the mass of Earth. Something orbiting at a distance of approximately 7.5 million kilometers. Now, 7.5 million kilometers sounds close. It is close. Mercury, the innermost planet in our solar system, orbits the Sun at roughly 58 million kilometers. Proxima b is far closer to its star than Mercury is to ours. At that distance around our Sun, the surface of any planet would be scorched. But Proxima is not the Sun. Proxima is dim. Proxima is cool. It puts out so little energy that 7.5 million kilometers from its surface sits comfortably inside what astronomers calculate to be its habitable zone. The zone where liquid water could, in principle, exist on a rocky surface. The proximity that would be lethal around a brighter star is, around this particular star, almost exactly right. That is a remarkable coincidence of physics. The picture did not hold. Proxima b is not alone. The system has siblings. In 2022, astronomers confirmed the existence of Proxima d, a planet with even less mass than Earth, orbiting even closer in than Proxima b, smaller and faster, hugging tight to the star in an orbit far inside the habitable zone. And in 2020, a third candidate appeared in the data, Proxima c, a possible planet at a much wider orbit, far outside the habitable zone. That one is disputed. The detection may reflect real physics, or it may be an artifact in the data, a ghost signal, a pattern that mimics a planet without actually being one. Whether Proxima c exists remains an open question, but Proxima b is not disputed. That signal is real. The minimum mass is real. The orbital period is real. An Earth mass world orbits in the habitable zone of the nearest star. That sentence is not a hypothesis. It is a measurement. And yet, here's what we do not know. We do not know whether Proxima b has an atmosphere. We cannot see it directly. We cannot measure its atmospheric composition. We cannot tell whether it breathes or whether it is bare rock. We do not know whether it has a magnetic field, the kind of invisible protective envelope that Earth carries, the structure that deflects the most energetic particles the Sun hurls toward us. And we do not know what the star has done to it. Proxima Centauri is an active flare star. This is not a gentle description. Proxima erupts. Periodically and without much warning, it releases bursts of ultraviolet radiation and X-rays far more intense than anything our sun routinely produces. These flares are not cosmetic. At the distance Proxima b orbits, they arrive at the planet's surface with real force. Over millions of years, a sustained bombardment of that intensity can strip a planet's atmosphere. Molecule by molecule, the upper atmosphere gets energized and ejected into space. If Proxima b lacks a strong magnetic field, there is no shield. The flares hit the surface directly. We do not know whether this has happened. We do not know whether the atmosphere, if one formed, survived. We do not know whether Proxima b was ever wet, ever warm in the way that matters for life. We cannot say whether it is a living world, a scoured rock, or something in between. Habitability is a hope. It is not a fact. The word appears in the scientific literature with qualifications and caveats layered around it like insulation. The announcement in 2016 did not fully carry those caveats into the headlines. So, this is where we actually stand. There is an Earth-mass planet in the habitable zone of the nearest star. That is real. Whether it is habitable is unknown. Whether it is dead is unknown. Whether it sits beneath open sky or beneath nothing at all is unknown. And still, the temptation is almost irresistible. The nearest star, an Earth-mass world, a habitable zone. The mind reaches for the next word almost automatically. Reachable. But that word is the one that deserves the most scrutiny. And what scrutiny actually reveals about the distance between us and that planet is something the announcement in 2016 also did not fully describe. Set habitability aside for a moment. Look at the number on its own, 4.24. It sounds contained, a decimal, a couple of digits, the kind of number you see on a road sign or a shipping estimate. It feels like something you could round up or round down and still capture the idea. But that intuition is exactly where the confusion begins. To the universe, 4.24 light years is almost nothing. The Milky Way stretches roughly 100,000 light years across. Andromeda, our nearest large galactic neighbor, sits about 2.5 million light years away. On those scales, the gap between us and Proxima Centauri is a rounding error. It barely registers. But we are not the universe. We are human beings who evolved to navigate a world of miles, hours, and arm's reach. A light year is not a unit built for human bodies. It is not a unit built for anything alive. It is the distance light travels in 1 year, moving at 299,792 kilometers per second. In a single second, light covers enough ground to circle Earth roughly 7.5 times. Let that sit for a moment. 1 second. 7.5 laps around the entire planet. At that speed, light passes the orbit of Mars in about 1 minute. It reaches the Sun in 8 minutes. It crosses Pluto's orbit in roughly 5.5 hours. 5.5 hours to reach the edge of the solar system, the farthest boundary of the world we have mapped and named and sent machines to visit. After Pluto, there is nothing familiar. No planet, no named landmark, just the cold dark of interstellar space stretching outward. And the next landmark is Proxima Centauri. 4 years, 2 months, and roughly 17 days of travel at the speed of light. 4 years of light. That is what separates us from the nearest star. Now translate it into kilometers. 1 light year is approximately 9.46 trillion kilometers. Multiply that by 4.24. The result is roughly 40 trillion kilometers. In miles, about 25 trillion. In astronomical units, the unit we use to measure distances within our own solar system, 4.24 light years works out to approximately 268,770 astronomical units. Those numbers are almost impossible to hold. So consider this instead. We have sent probes into space, real machines, launched by real rockets, traveling at real speeds. Voyager 1 launched in 1977. It is the most distant human-made object ever built. After nearly 5 decades of continuous travel, it sits roughly 165 astronomical units from Earth. 165 astronomical units. That is extraordinary. It took almost 50 years to get there. Proxima Centauri is at 268,000 astronomical units. Not 268, not 2,680, 268,000. Voyager 1 travels at about 17.3 kilometers per second. That is roughly 62,000 kilometers per hour, around 550 million kilometers per year. At that speed, the time it would take to reach Proxima Centauri is approximately 73,000 years. 73,000 years. Recorded human civilization is somewhere around 5,000 to 7,000 years old, depending on how you count it. Writing, cities, agriculture, the full arc of everything we call history. Voyager 1, our farthest and fastest long-duration traveler, would need to cover a span roughly 10 times that entire history before it reached the nearest star. It would still be traveling when whatever comes after civilization has also come and gone. But Voyager 1 is not our fastest spacecraft. In 2018, NASA launched the Parker Solar Probe. Its mission is to study the sun, and to do that, it skims the solar corona at extraordinary speeds. At its closest approach to the sun, the Parker Solar Probe reaches a peak speed of approximately 191 kilometers per second. That is roughly 690,000 kilometers per hour. Here is what that means in terms you can feel. At that speed, Parker could cover the distance from New York to Los Angeles in about 20 seconds. 20 seconds. The answer was stranger than expected. Even Parker, moving at the fastest speed any human-made object has ever achieved, would take approximately 6,700 years to reach Proxima Centauri. 6,700 years. The Great Pyramid at Giza was built roughly 4,500 years ago. Parker, at peak speed, would still be traveling after that much time had passed. Consider the full sweep of ancient Egypt, ancient Greece, the Roman Empire, the Middle Ages, the Renaissance, the Industrial Revolution, and the entire space age, stacked end to end. That combined span runs somewhere around 6,000 years. Parker would need longer than that. Longer than all of it, repeated nearly 3 times over. And there is one more thing to know about Parker's speed. It only reaches that peak velocity briefly during its closest approach to the sun. The intense gravity of the sun is what accelerates it to those speeds. In the cold of interstellar space, with no sun to slingshot around, Parker would carry only the velocity imparted at launch. It would travel far slower than 191 kilometers per second for the vast majority of any interstellar journey. The 6,700-year figure assumes constant peak speed. The real number would be worse. Every probe we have ever launched, every spacecraft that has ever left Earth, has remained within approximately 50 astronomical units of our planet. 50. Voyager 1, after almost 5 decades, has traveled 165 astronomical units, and Proxima sits at 268,000 astronomical units. That is not a gap. It is a chasm. Think of it this way. Imagine standing on a Pacific shoreline, looking west, and knowing the nearest land is 5,000 miles across open water. No boat, no fuel, no way to swim it. You know the land is there. You can even describe what it looks like. But nearest does not mean near. Nearest is a ranking, not promise. It tells you which direction. It does not tell you the crossing is possible. That is where we stand. The number 4.24 is real. The distance it describes is real, and the machines we have built, at the absolute limits of current engineering, cannot make the crossing in any time frame that resembles a human mission. The physics of the distance has not changed, only our sense of what the number means has, and understanding what it actually means is where any honest conversation about reaching Proxima Centauri has to begin. Whether there is any path forward from here is the question we have not yet opened. And yet, even after seeing those numbers, the word nearest keeps pulling at something in us. It keeps suggesting that a crossing is imaginable, that it is simply the next step in a long line of steps we have already taken. That pull is not random. It comes from a pattern that has been true for almost all of human history. We reached the ocean, then we crossed it. We reached the poles, then we stood on them. We reached for the moon, then we landed on it. Each frontier, in time, became a passage, and the mind, trained on that history, looks at the stars and sees the same shape. The nearest star, the next frontier, the next chapter. But the analogy fails. Every single frontier we have ever crossed was inside the same gravitational neighborhood, the same system, the same local physics. The oceans are on Earth, the poles are on Earth, the moon orbits Earth, Mars orbits the same sun. The Voyager probes, even now, are still inside the heliosphere, still inside the bubble of influence that our sun broadcasts outward into space. Every passage in human history, every ocean crossing, every polar expedition, every rocket launch, every probe we have ever sent has happened inside a pocket of the cosmos that is, by the measure of what lies beyond it, almost impossibly small. Proxima Centauri is not in that pocket. The distance ladder makes this concrete. The moon is 1.3 light seconds away. Mars, at its closest approach, is roughly 3 light minutes. The Voyager probes, the farthest objects we have ever launched, are about 22 light hours from Earth. Nearly 50 years of flight, 22 light hours. Now hold those numbers next to each other. Light seconds, light minutes, light hours. The progression feels gradual. It feels like a ladder with manageable rungs. Proxima Centauri is 4.24 light years away. Not light hours, light years. That single unit change is not a step up the ladder. It is the ladder ending and a cliff face beginning. If you were to draw those distances on a graph, the Moon, Mars, and the Voyager probes would cluster so tightly near the bottom that you could barely separate them. And then the line would shoot upward, nearly vertical, to reach Proxima. 3 orders of magnitude. That is what the jump from light hours to light years means. It is not a continuation. It is a discontinuity, a different kind of distance altogether. And that word, nearest, does none of this work. It performs a ranking. It tells you that among the hundreds of billions of stars in the Milky Way, Proxima Centauri finished first in a sorting exercise based on distance from our sun. That is all. It says nothing about the size of that distance. It says nothing about whether a crossing is possible. It says nothing about what tools you would need. It simply names the winner of a list ordered by proximity, and then it steps back, and it lets your brain fill in the rest. Your brain fills in the rest with a history that does not apply. Go back to the shoreline. You are standing at the edge of the Pacific, looking west, and the nearest land is 5,000 miles across open water. You have no boat, no fuel, no way to swim it. The word nearest is technically accurate. That land is the closest land in that direction, but the word is doing something to you. It is making the land feel like a destination rather than a direction. It is letting you feel the pull of the other side without giving you any honest accounting of what the crossing requires. That is what nearest star does. It names a direction, it creates a feeling, and it quietly omits the physics. The physics is this: every tool and techniques that carried humanity across its previous frontiers was built for the distances inside this pocket. The chemistry of rocket fuel is calibrated to Earth's gravity well and planetary distances. The engineering of deep space probes was designed for journeys that measured in years, not millennia. The fastest object we have ever built would need thousands of years to approach Proxima, and it only reached that speed because it swung close to the Sun and borrowed gravity for a brief acceleration. In open interstellar space, no such loan is available. Not one system, not one technology, not one method we currently possess was designed for a gulf measured in light years. All of it was built for the curve at the bottom of the graph. None of it was built for the cliff. So when we say Proxima Centauri is the nearest star, we are telling the truth. It is the nearest. But the word carries an implication it cannot support. It implies that nearness translates to accessibility, the way it has for every frontier before this one. It implies that the pattern holds, that the next chapter looks like all the previous chapters. It does not. The crossing to Proxima is not the next chapter in human exploration. It is something that does not yet have a chapter. It requires tools that do not exist, timescales that exceed anything we have ever planned for, and a rethinking of what the word mission means at distances where every assumption built into that word breaks down. What those tools might look like and whether any of them are real is where this story has to go next. The tools do not exist yet. That is the honest answer. But before we can understand why, we have to go one level deeper. We have to ask what physics is actually doing underneath all of that. Because the problem with reaching another star is not simply that our rockets are not powerful enough. It is that the mathematics of motion makes conventional rocketry impossible at interstellar speeds. Not difficult, not expensive, impossible. And understanding why that is true changes everything about how you think about the problem. Start with kinetic energy. The energy an object carries as it moves depends on two things: its mass and its velocity. Mass is straightforward. Velocity is not. The relationship between speed and energy is not linear. It scales with the square of velocity. That means doubling your speed does not double your energy cost. It quadruples it. Triple your speed, and the energy cost multiplies by 9. The faster you go, the more punishing each additional increment of speed becomes. Now apply that to the target. To reach Proxima Centauri in any time frame that resembles a human mission, a spacecraft would need to travel at a significant fraction of the speed of light. The most commonly discussed target is 10% of light speed. That is roughly 30,000 kilometers per second. To put that in terms of our fastest probe, Voyager 1 currently travels at about 17 kilometers per second. 10% of light speed is approximately 1,700 times faster than that. Not twice as fast. Not 10 times as fast. 1,700 times faster. The energy required to push even a modest spacecraft to that speed, at perfect efficiency, with no fuel mass penalty and no reserves for braking or course correction, is comparable to the total annual energy consumption of an entire nation. That is the flaw. The actual cost would be far higher, and the energy is only half of it. Even if you could somehow produce that energy, you still face a second problem. And this one is older. It was worked out in 1897 by a Russian school teacher and mathematician named Konstantin Tsiolkovsky. He derived what is now called the rocket equation. It describes the relationship between three things: the speed of gas expelled from the engine, the ratio of fuel mass to final vehicle mass, and the change in velocity you can achieve. The relationship is exponential. That word matters. Exponential does not mean steep. It means that as your target velocity increases, the required fuel mass does not grow proportionally. It grows by compounding multiplication. Every increment of additional speed demands a larger and larger multiple of fuel. Here is what that looks like in practice. A chemical rocket expels gas at roughly 3 to 4.5 kilometers per second. That is the exhaust velocity. It is the fundamental limit of the chemistry. And because the rocket equation is exponential, there is a hard consequence. To reach interstellar speeds using chemical propulsion, the fuel mass required would exceed the payload mass not by a factor of 10, not by a factor of 100, but by factors of thousands or millions. The numbers do not converge on a solution. They spiral away from one. The reason is the fuel spiral. Every kilogram of fuel you add to reach a higher speed is itself a kilogram that must be accelerated, which means you need more fuel to carry it, which adds more mass to be accelerated, which requires more fuel. The spiral compounds. At some point, no quantity of onboard fuel can reach the destination because the fuel itself has become the dominant burden. Nuclear thermal rockets were proposed as a way to break that ceiling. They use a nuclear reactor to superheat a propellant, producing exhaust velocities roughly twice those of chemical engines. That sounds like progress. It is not enough. Twice the exhaust velocity helps, but the exponential character of the rocket equation does not change. The spiral still runs away. Nuclear thermal rockets are a genuine improvement for missions within the solar system. For interstellar distances, they cannot escape the trap. This is not a budget problem. It is not a political problem. It is not a problem that disappears if we wait for better manufacturing. It is a problem in the mathematics of propulsion. The rocket equation is not an engineering approximation. It is physics. And it says unambiguously that conventional rocketry cannot reach another star. This is why every serious proposal for interstellar travel abandons onboard chemical or nuclear thermal engines entirely. Nuclear pulse propulsion, fusion drives, antimatter propulsion, laser push sails. Each of those concepts attacks the problem from a different angle. None of them are simple. None have been built or tested at scale. We will come to each of them, but the reason they all appear on the list is the same reason. The rocket equation rules out the conventional path. Now, there is one family of engines that is sometimes raised as a counterexample: ion engines and plasma drives. These are real, proven technologies, and in one specific way, they are genuinely superior to chemical rockets. The advantage is exhaust velocity. A typical ion thruster ejects propellant at speeds of 20 to 50 kilometers per second. Advanced plasma engines, still largely experimental, could push that to hundreds of kilometers per second. Those numbers dwarf the 3 to 4 kilometers per second of chemical rockets. Higher exhaust velocity means you extract more change in velocity from every kilogram of propellant. The rocket equation rewards that. Ion engines use their fuel far more efficiently than anything that burns chemicals. That efficiency is not theoretical. NASA's Dawn mission demonstrated it in the real world. Launched in 2007, Dawn used ion propulsion to orbit two completely separate bodies in the asteroid belt, Vesta and then Ceres. That mission was impossible with chemical rockets. The fuel requirements would have been unmanageable. Ion propulsion made it feasible. Dawn remains one of the most elegant demonstrations of what electric propulsion can do in the solar system. But there is a limit, and it is fatal for interstellar travel. thrust. An ion engine produces force measured in fractions of a newton. Hold a sheet of paper flat on your open palm. The weight of that sheet pressing down on your hand is roughly comparable to the thrust a typical ion engine produces. That is not a misstatement. That is the actual number. VASIMAR, the variable specific impulse magnetoplasma rocket, represents some of the most optimistic projections for advanced plasma propulsion. In its most favorable configurations, it might produce a few newtons of thrust, a few sheets of paper. These engines work by firing for months and years continuously, building speed gradually. For missions inside the solar system, where travel times of a year or several years are acceptable, that approach is effective. But the math at interstellar distances is unforgiving. Reaching 1% of light speed, which is 3,000 kilometers per second, using ion engine thrust levels would require decades of continuous burning. Reaching 10% of light speed would require centuries of continuous thrust. And to sustain that kind of burn for that long, you would need onboard power far beyond any reactor that has ever flown, or is likely to fly. Electric propulsion makes a trade. It exchanges thrust for efficiency. For the solar system, that is an excellent trade. The solar system rewards patience. A mission that runs for 3 years instead of 6 months is acceptable when the destination is Jupiter or the asteroid belt. But the gulf between stars does not reward patience. It punishes it. A mission that would take centuries of continuous burn to reach 1% of light speed, and then centuries more to reach 10%, is not a slower version of a solar system mission. It is a different category of problem entirely. The math is not the budget. The math is not the timeline of current technology. The math is the wall. Chemical rockets, nuclear thermal rockets, and electric propulsion all run into versions of the same wall. The specific location of the wall differs. The wall itself does not move. What that means is this: the next propulsion paradigm does not save us. Ion engines and plasma drives are not a stepping stone to the stars. They are a better way to explore the solar system. That distinction matters. The tools that make Dawn possible, the tools that might someday accelerate cargo through the inner planets, are built for a different problem than the one posed by 4 light years of open space. And the concept that might actually address that problem, that might genuinely bend the mathematics towards something workable, are stranger, more ambitious, and more uncertain than anything we have built so far. So let's put a number on it. 1 mission, 1 ship, 1 attempt to accelerate toward Proxima and slow down on the other side, and watch what the joules become. The ship we are imagining is not lavish. It is the minimum a crewed interstellar mission would plausibly require. Shielding against decades of radiation exposure, life support systems that cannot fail, habitats for several hundred people across a journey measured in generations, repair infrastructure because nothing can be sent from Earth on any useful timeline, and fuel reserves for deceleration because a ship that cannot slow down is not a mission. It is a death sentence pointed at another star. At departure, this minimum ship weighs roughly 50,000 tons. That is before we account for the fuel it carries, before propulsion, before anything that actually moves it, just the vessel and the people and the systems they need to stay alive. Now accelerate that ship to 10% of the speed of light. The kinetic energy required is approximately 2.25 times 10 to the 22nd power joules. That notation means little on its own, so let's give it something to stand next to. Earth's total annual energy production from every source, every power plant, every turbine, every solar panel, every reactor on the planet adds up to roughly 5.8 times 10 to the 20th power joules per year. Here is what that comparison produces. The kinetic energy required just to accelerate this ship to 10% of light speed equals roughly 39 years of total global energy production. Every nation, every city, every machine that runs on power anywhere on Earth, running continuously for nearly 4 decades, producing nothing else, devoted entirely to pushing one ship up to speed. And that is only the acceleration. The ship has to stop. At Proxima Centauri, there is no infrastructure waiting, no gravitational slingshot available in the right direction, no braking system built into the destination. The ship must carry everything it needs to decelerate, and decelerate by burning that fuel. The energy required to slow the ship from 10% of light speed to a manageable orbital velocity is approximately what it took to accelerate it in the first place. Another 2.25 times 10 to the 22nd joules. Another 39 years of global output. Round-trip kinetic energy alone, just the accel and the decel, comes to roughly 4.5 times 10 to the 22nd joules. Approximately 78 years of everything the entire planet produces. Not 78 years of one nation's output. Not 78 years of the largest economy ever built. 78 years of everything, every watt generated anywhere on Earth, diverted to a single mission. And that figure does not include powering the life support systems across the transit. It does not include food production, lighting, communications, navigation, or any of the continuous energy demands of keeping several hundred people alive for decades. It covers only the kinetic work of moving the ship and stopping it. But here is where it gets strange. That number, staggering as it is also not the real number. The real number is far larger. And the reason goes back to the rocket equation. To decelerate the ship at Proxima, you must carry the fuel for deceleration with you from Earth. But that fuel has mass, and that mass must be accelerated to 10% of light speed along with everything else, which means you need additional fuel to accelerate the deceleration fuel, and that additional fuel has its own mass, which requires still more fuel to accelerate it. The spiral does not converge. Each layer of fuel demands another layer beneath it, and the mass you must move at departure grows with each iteration. This is the exponential trap, the same spiral described by the Tsiolkovsky equation, now applied to the full round-trip energy budget. The total propulsive energy required for a realistic crewed mission does not exceed the payload kinetic energy by a small margin. It exceeds it by factors of hundreds to thousands, depending on the engine efficiency and the mission profile. The fuel mass at departure for a mission like this reaches into the millions of tons. Not the ship, not the payload, the fuel alone. Millions of tons of propellant that must itself be accelerated, carried, and eventually burned, consuming energy on a scale that recalibrates the meaning of the word civilizational. This is why no brute force approach has ever produced a viable crewed interstellar architecture. Engineers have run the numbers for chemical propulsion. They have run them for nuclear thermal designs. They have run them for advanced electric drives. Every time the mission profile includes a crewed vessel, a meaningful payload, and a deceleration requirement at the destination, the fuel spiral overwhelms the concept. The energy demand does not land in a range that any foreseeable version of human civilization could supply on any reasonable timeline. The math is not describing a difficult mission. It is describing a structurally impossible one, given the tools we have discussed. The exponential trap does not get easier with more engineering investment. It gets harder because the more mass you add to solve one problem, the more mass you must accelerate to carry that solution. What remains then is a question the numbers have been pointing toward across every section of this journey. If conventional propulsion cannot reach another star, and if the energy demands of brute force approaches exceed civilizational output by decades, then the only path forward requires abandoning not just the rocket equation, but the entire physical framework it describes. The concepts that might genuinely address the problem do not look like anything we have built, and whether any of them can survive contact with reality is the question the next generation of physics will have to answer. So if brute force cannot do it, what has actually been studied as an alternative? That question has been asked seriously, by serious people, for decades. The answers they produced are not science fiction. They are engineering proposals grounded in real physics, with real numbers attached. And what those numbers reveal is something more complicated than a simple solution. Every exotic concept either hits a political wall, an unsolved physics problem, or a production constraint so severe it effectively does not exist yet. The entry point is nuclear fission. A kilogram of fissile material releases roughly 80 trillion joules of energy. That is approximately 8 million times the energy density of chemical propellants. The difference is not marginal. It is the difference between a candle and a furnace the size of a city block. In 1958, a team at General Atomics took that energy seriously in the most direct way anyone has ever proposed. Ted Taylor and Freeman Dyson conceived Project Orion. The concept was this: detonate nuclear bombs behind a massive pusher plate and ride the shockwave forward. Not a metaphor, not a theoretical model, a spacecraft driven forward by a continuous series of nuclear explosions at its rear. Dyson worked out an interstellar version using deuterium fusion pulse units. The exhaust velocity would reach roughly 15,000 kilometers per second. Delta V, the total change in speed available to the ship, would approach 20,000 kilometers per second, about 6.7% of the speed of light. At that velocity, the flight time to Alpha Centauri would be approximately 130 years. Thermonuclear variants pushed the ceiling higher. Top cruise velocities of 8 to 10% of light speed appeared achievable, though without any reserve for braking. The vehicle mass would be around 100,000 tons. It would require millions of pulse units. The physics was valid. No fundamental law of nature prevented it. In 1963, a piece of paper stopped it. The Partial Nuclear Test Ban Treaty prohibited nuclear detonations in the atmosphere and in space. Orion was over as a practical program. The physics remains valid today. The treaty remains in force. The British Interplanetary Society took the next serious step between 1973 and 1978. Project Daedalus examined what a fusion-powered interstellar probe might actually look like on paper. The concept used inertial confinement fusion, small pellets of deuterium and helium-3 ignited by high-power electron beams at a rate of roughly 250 microdetonations per second. The spacecraft would be two-stage, with a total launch mass of about 54,000 tons. The first stage carried 46,000 tons of fusion fuel. The second stage carried 4,000 tons. The mission target was Barnard's star, about 6 light-years away. The cruise velocity reached approximately 12% of the speed of light, around 36,000 kilometers per second. Flight time to Barnard's star, roughly 50 years. But the reality was different. Daedalus included no deceleration system. The ship would scream past Barnard's star at 36,000 kilometers per second and keep going. That design choice was not an oversight. It was a consequence of the fuel requirement. Adding enough propellant to slow down would have made the mission mass impossible to justify. A probe that cannot stop is a significant scientific limitation. But the fuel problem was even more fundamental than that. Daedalus required helium-3 in quantities that exceeded the entire global supply available on Earth. The solution proposed in the study was to mine helium-3 from Jupiter's atmosphere using giant balloon platforms suspended in the upper cloud layers. That is not a small engineering footnote. That is a civilization-scale prerequisite, requiring technologies that do not exist, operating at a planet we have never landed on, to produce fuel for a ship we have never built, to send an unmanned probe past a star without stopping. Fusion propulsion in general holds genuine theoretical promise. Fusion releases roughly 3 to 4 times more energy per kilogram than fission. Theoretical exhaust velocities for fusion drives range from 10,000 to 30,000 kilometers per second. At the upper end, a flyby of Proxima could take a few decades. A mission with full deceleration might be accomplished in a century or less. Those numbers are real. The problem is that they describe what fusion propulsion would do if it existed. As of 2026, no fusion reactor anywhere in the world produces sustained net energy. Not one. The largest fusion project ever built is ITER, under construction in southern France, a collaboration among 35 nations. The ITER tokamak, the magnetic confinement vessel at the core of the reactor, has a mass of roughly 23,000 tons. The vacuum vessel is more than 11 meters tall and about 20 meters in outer diameter. The cryostat surrounding it spans approximately 30 meters across. The plasma inside operates at temperatures exceeding 150 million degrees Celsius, hotter than the core of the sun, held in place by superconducting magnets cooled to near absolute zero. The system requires hundreds of megawatts of external power just to run the magnets and heating systems. Deuterium-tritium experiments capable of demonstrating net energy production are now scheduled for around 2039 under the most recently revised timeline. ITER produces heat. It is a power plant prototype, not a propulsion system. But here is the harder problem. Converting ITER into a spaceship engine is not a matter of scaling. It is reinvention. A space-rated fusion engine must convert fusion energy into directed exhaust. It must be compact and light. It must operate continuously, or in high-performance repeated burns, for years without maintenance. It must manage neutron flux, the stream of high-energy particles that gradually degrade structural materials, with no replacement parts available. It must confine plasma hotter than the sun's core inside a magnetic bottle that cannot fail ever on a mission lasting decades. And it must radiate enormous quantities of waste heat into vacuum, where there is no air and no water to carry heat away, which requires large radiator panels adding mass to a system that must simultaneously be as light as possible. These are not refinements of what ITER does. They are different problems. Consider the development timeline of other propulsion technologies. Jet engines took roughly 20 years to travel from laboratory concept to operational service. Liquid-fueled rockets took approximately 30 years from Robert Goddard's early experiments to the capability to reach orbit. Both of those development paths began with the working demonstration of the underlying principle. Fusion propulsion begins from no demonstrated net energy gain. Its development path is longer, not shorter, and considerably more uncertain. Antimatter sits at the far end of the energy spectrum. Matter-antimatter annihilation converts 100% of mass into energy. The energy density is roughly 300 times that of fusion. Theoretically, a few hundred grams of antimatter could accelerate a spacecraft to a significant fraction of the speed of light. Wait, a few hundred grams? That number sounds small. It is not. Here is the actual production figure. The total quantity of antimatter that humanity has manufactured across every particle accelerator ever built, across the entire history of particle physics, is approximately 20 nanograms. Not 20 grams, not 20 milligrams, 20 nanograms, which are billionths of a gram. CERN's ALPHA experiment recently achieved a landmark: more than 15,000 antihydrogen atoms trapped simultaneously. That is a genuine scientific achievement. It is also a quantity measured in trillionths of a gram. Producing even a few grams of antimatter would require accelerator infrastructure thousands of times larger than anything currently in existence, running for years, consuming energy at rates exceeding national power grids. Storing it presents a separate problem that is not easier. Antimatter cannot touch ordinary matter without annihilating instantly. Charged antiprotons have been stored in magnetic traps for over a year in laboratory settings. Storing the gram-scale quantities needed for propulsion in containers that must survive launch, radiation exposure, thermal cycling, and years of operation in deep space is not a near-term engineering challenge. It is beyond anything current engineering can project a path toward. And even setting aside production and storage, antimatter propulsion is not perfectly efficient. The annihilation reaction produces neutrinos, which pass through any shielding and carry their energy away uselessly. It also produces gamma rays, which require massive shielding to manage. The practical fraction of total annihilation energy that can actually be captured and directed as thrust is estimated at roughly 40%. The remaining 60% becomes waste heat and radiation, not the ultimate fuel, the most powerful fuel imaginable, trapped behind the hardest engineering problems anyone has ever identified. The pattern across all three exotic approaches is the same. Nuclear pulse propulsion is physically validated, but politically and environmentally blocked, and it required vehicle masses and fuel supplies that strain any realistic conception of what a mission could look like. Fusion propulsion is the most frequently cited hope for reaching another star. Yet controlled fusion remains unsolved in 2026, and a flight-rated fusion engine is a reinvention problem starting from no demonstrated net energy gain. Antimatter has the highest energy density of any known substance, and humanity has produced roughly 20 nanograms of it across the entire span of modern science. Every exotic concept survives scrutiny on paper. Every one of them, when pressed against physical reality, reveals a harder, unsolved problem sitting directly beneath it. The question of how to cross interstellar distances keeps arriving at the same place. The biggest obstacles have not been touched yet, so that leaves one more question. If onboard propulsion is the bottleneck, what happens when you remove it entirely? That was the idea behind Breakthrough Starshot. Not a different kind of engine, a fundamentally different architecture. Leave the energy source on the ground. Use it to push the spacecraft from behind across millions of kilometers of empty space using nothing but light. The concept was announced in 2016 by a coalition of scientists and funders, including Stephen Hawking and Russian billionaire Yuri Milner. The core design was elegant in the way that only the most reduced ideas can be. A phased laser array on the ground would generate roughly 100 gigawatts of directed power. That is approximately the combined output of 100 large nuclear power plants, all focused into a single coherent beam. The beam would strike a reflective sail roughly 4 meters across, about the size of a large room. Attached to that sail, a gram-scale electronic package called a star chip, a camera, a power source, navigation, a laser transmitter capable of sending signals home across 4.24 light years. The photon pressure from the beam would accelerate the sail to roughly 20% of the speed of light in about 10 minutes. The acceleration forces involved are tens of thousands of times Earth gravity. No human being could survive them. No conventional structure could survive them. That was part of the elegance. There was no crew to protect. At 20% of light speed, the craft would reach Proxima Centauri in roughly 21 years. The flyby itself would last only hours. A chip and a camera flung past the nearest star, capturing images during a window that closes almost as soon as it opens, then transmitting those images home over years of signal travel time. And what made this genuinely clever was what it abandoned. Every propulsion concept examined before this one had to carry its energy source along. That is what the rocket equation punishes. Starshot moved the energy source off the vehicle entirely. The laser stays on the ground. The sail carries no fuel. The payload is measured in grams, not tons. By eliminating onboard propulsion, the required energy drops by orders of magnitude compared to any crewed architecture. By eliminating deceleration, it drops further still. That last choice deserves a moment. Deceleration costs nearly the same energy as acceleration. For a vehicle carrying its own fuel, stopping at the destination roughly doubles the fuel requirement. And then the rocket equation compounds that doubling into something far worse. A crewed vessel needing 50,000 tons of fuel to accelerate might need hundreds of thousands of tons to slow down at arrival. Starshot simply chose not to slow down. One way, no braking, no orbit, no landing. A flyby at 60,000 kilometers per second. What other missions called a critical flaw, Starshot called a design choice. There are alternative braking concepts. Magnetic sails that drag against the thin medium of interstellar gas. Photon pressure braking that uses the light of the destination star itself to slow an incoming craft. Each has severe limitations that we will come to. For now, the point is that no proven deceleration method exists for any interstellar vessel, crewed or otherwise. Starshot sidestepped the problem entirely by accepting a flyby as the mission. It was the minimum viable interstellar concept. The flaw of what could count as a mission to another star. But something was wrong. Even the flaw proved unreachable. The engineering challenges did not emerge gradually. They were visible from the beginning, and they did not shrink with time. Start with the laser array. 100 gigawatts of coherent, phase-locked light, focused tightly enough to illuminate a 4-meter sail at distances of millions of kilometers. Coherent means all the individual laser elements must be synchronized with extraordinary precision. Their wavefronts aligned so they combine into a single unified beam rather than scattering into uselessness. Laboratory demonstrations achieved phase locking across tens of laser elements. Scaling that to the millions of coherent elements required for 100 gigawatts has no clear solution path. Not a difficult path, not an expensive path, no established path at all. The physics of atmospheric distortion alone, the way air turbulence bends and scatters light, would require adaptive optic systems of a kind never built and never seriously prototyped at this scale. Then the sail. It must weigh only grams across 4 square meters of surface. It must reflect nearly all of the incident light rather than absorbing it, because absorbed energy becomes heat, and heat at 100 gigawatts of input would vaporize any material that absorbed even a small fraction of the beam. It must survive accelerations of tens of thousands of Gs without tearing. Caltech and other institutions explored ultra-thin silicon nitride membranes as candidate materials. The research was real and technically serious. No full-scale sail was ever built. The material requirements pushed against the physical limits of what thin films can tolerate, and the manufacturing challenges of producing gram-mass sails at 4-meter scales had no industrial precedent than the Starship itself. A few grams carrying a camera with enough resolution to return useful images of a planetary system during a flyby of hours. A power source capable of operating for 21 years in interstellar space. Navigation precise enough to direct the sail through a beam millions of kilometers away. And a laser communication system capable of transmitting a coherent signal across 4.24 light years to be detected back on Earth. All of it in grams. All of it surviving the crushing acceleration of launch. All of it functioning after 2 decades of cosmic ray bombardment in open space. Each of these requirements, taken alone, represented a significant engineering challenge. Together, they represented a program that would require simultaneous breakthroughs in laser physics, materials science, nanotechnology, and communications engineering, none of which had established timelines. In September 2025, Scientific American reported the outcome. After 9 years of work, Breakthrough Starshot entered the indefinite hold. The program had spent approximately $4.5 million of an originally pledged $100 million. Less than 5% of the committed funding had been deployed. No integrated prototype existed. No credible construction timeline had been produced. Estimates for the final mission cost, assuming all the required breakthroughs were eventually achieved, ran between $5 and $10 billion. 9 years, $4.5 million. No prototype, indefinite hold. This was the minimum viable interstellar mission. No crew, no life support, no food, no water, no air, no shielding against radiation, no deceleration system, no return. Just a gram-scale chip and a camera, flung past the nearest star at 1/5 of the speed of light, with an encounter window measured in hours. That was the version that proved too hard. A crewed mission to Proxima Centauri requires everything Starshot required, and then orders of magnitude more. It needs the energy to accelerate not grams, but tens of thousands of tons. It needs a way to slow down at arrival. It needs shielding against decades of radiation exposure. It needs life support, food production, water recycling, medical infrastructure, and human habitats capable of functioning for the duration of a journey lasting decades or longer. It needs a crew that can survive, remain capable, and complete a mission that spans more time than most human careers. Starshot was built to answer a simpler question: can we reach the nearest star at all, even in the most minimal sense, even with no one aboard? The answer, after nearly a decade of serious effort, was not yet. The harder question, the one this journey has been building toward, is what it would actually take to send people there, and whether the gap between today's engineering and that requirement has any plausible path across it. The answer begins with a problem Starshot chose to ignore. The deceleration problem is waiting. But before we arrive at it, we need to step back and ask a question that has been quietly underneath all of this. Even if some future propulsion technology does mature, even if fusion drives or nuclear pulse systems or something we have not yet imagined eventually become real, what does the journey actually look like in years? Not in light years, not in abstract fractions of the speed of light. In years, human years, the kind that age a person, raise a child, outlast a career. The answer depends entirely on how fast you can go. Start with the most optimistic scenario anyone has seriously proposed. Assume that fusion propulsion matures within the next 50 to 100 years. Assume the engineering challenges get solved, the fuel gets sourced, the systems get miniaturized for spaceflight. A fusion drive of that kind could produce an exhaust velocity of roughly 15,000 kilometers per second. That is as 5% of the speed of light moving through the engine nozzle. With that exhaust velocity and reserving enough fuel to slow down at arrival, a ship could cruise at around 10% of the speed of light. At 10% light speed, the transit to Proxima Centauri takes approximately 42 years. Add the acceleration phase at departure and the deceleration phase at arrival, each lasting months to years, and the total mission duration comes to roughly 45 to 50 years. 45 to 50 years. That is the optimistic case, built on technologies that do not yet exist. Now shift to more conservative assumptions. Nuclear pulse propulsion, the Orion-style concept covered earlier, could reach a cruise velocity of around 5% of light speed. At that pace, the transit to Proxima alone takes approximately 85 years. Add acceleration and deceleration, and the total reaches 90 to 100 years. That is not a single lifetime. That is a voyage that begins with one generation and ends with another. The crew that arrives is not the crew that departed. Their grandchildren might be the ones to see the destination for the first time. Pull the velocity down further. At 3% of light speed, transit time exceeds 140 years. At 1% of light speed, which is still roughly 3,000 kilometers per second, far beyond anything humanity has ever built, the journey takes more than 420 years. And every one of these numbers assumes something that has never been achieved. They assume flawless propulsion over decades. No failures, no degradation, no unexpected system loss. They assume solved navigation, solved deceleration, sufficient fuel carried from the start. They assume sustained institutional commitment for the full duration of this mission, from launch through arrival. Every number is already the best version of the story, and they apply only to Proxima Centauri. Every other star is farther. Most are incomparably farther. Something else was happening. Even granting all of that, even granting that we somehow built the ship and sourced the fuel and solved the deceleration, there is a deeper problem that no propulsion system resolves by itself. It is a problem about when to launch. In 2006, researcher Andrew Kennedy formalized what is now called the weight calculation. The logic is simple and devastating. If you launch a mission today at the best available speed, a faster mission launch 10 or 20 years from now might overtake you and arrive first. Propulsion technology improves over time. A ship that leaves later, moving faster, could pass a ship that left earlier, moving slower, somewhere in the void between the stars. This means the rational strategy is to wait. Wait for better propulsion. Wait until the technology improves enough that launching becomes clearly optimal rather than clearly premature. But applied consistently, that logic never terminates. There is always a better engine on the horizon, always a reason to wait one more decade. The same calculation that says you should wait also says you should keep waiting, because the next improvement is always coming. Applied without limit, the wait calculation produces a civilization that never launches at all. Think of it like a laptop purchase deferred indefinitely because a better model is always 6 months away. Reasonable each time, paralyzing across years. Kennedy's analysis suggested that the optimal departure window for a crewed interstellar mission to Proxima lies somewhere between several decades and roughly a century in the future, depending on how fast propulsion technology actually improves. Not today, not yet, but also not infinitely deferred. There is a window. The problem is knowing when you are in it, and whether any institution will still be functioning and committed when that window arrives. Which brings us to the hardest part of all of this. Not the physics, not the fuel, the institution. We struggle to sustain space program commitments across even 2 decades. The James Webb Space Telescope, one of humanity's most ambitious scientific instruments, took approximately 25 years from initial concept to launch. That is a remarkable achievement. It is also, by the standards of an interstellar mission, a short sprint. The International Space Station has been continuously occupied since the year 2000. Its planned operational lifespan is roughly 30 years. It depends on regular resupply missions. It depends on continuous international cooperation. It depends on annual funding decisions made by governments that change, priorities that shift, and economies that cycle. Neither project comes within orders of magnitude of what a crewed interstellar mission would require. Not in duration, not in institutional continuity, not in the kind of civilizational commitment that would need to outlast political cycles, economic crises, and generational shifts in what humanity decides to care about. The interstellar problem is not just an engineering problem. That is the reveal. It is a problem of civilizational time. It is the relationship between physics, engineering capability, institutional endurance, and the simple fact that some commitments require a kind of patience that no institution in human history has ever demonstrated. We can build the equations, we can imagine the ships. We have not yet built the kind of civilization that could sustain the mission those equations describe. The propulsion question and the weight calculation and the institutional question are all pointing at the same thing. Getting to Proxima is not a matter of picking the right engine. It is a matter of becoming a different kind of civilization first. And that problem does not have a launch date yet. What happens if we actually try to solve the deceleration problem specifically is where the next layer of difficulty lives. Set the institutions aside for a moment. Set aside the political cycles and the funding gaps and the generational patience that no civilization has ever demonstrated. Assume, for argument's sake, that all of it is solved. The propulsion works, the deceleration works, the money holds, the mission launches. Now ask a different question. What happens to the people inside? A gram-scale probe does not eat. It does not breathe. It does not get cancer, or lose bone density, or panic in the dark, or grieve someone who died 3 years into the crossing. It does not need a doctor, or a harvest, or a reason to keep going. A crewed mission does. Every single one of these things. And the gap between a robotic mission and a human one is not a matter of degree, it is a matter of kind. The biology is a separate problem from the propulsion. And in some ways, it may be the harder one. Start with radiation. In space, beyond the protective envelope of Earth's magnetic field and atmosphere, the environment is flooded with galactic cosmic rays. These are high-energy protons and heavier atomic nuclei, accelerated to significant fractions of the speed of light by supernovae and the violent cores of distant galaxies. They do not behave like sunlight. They penetrate, they ionize atoms along their path, breaking molecular bonds, damaging DNA, and triggering cascades of secondary particles inside tissue. Here is the dose ladder. On Earth's surface, the average person absorbs roughly 2.4 millisieverts of radiation per year. A millisievert is a unit measuring the biological effect of absorbed radiation. Astronauts on the International Space Station absorbed somewhere between 160 and 320 millisieverts per year, depending on the solar cycle. That is a meaningful elevation, but it is manageable within carefully tracked career limits. Beyond planetary fields, in interstellar space, unshielded exposure climbs to roughly 400 to 600 millisieverts per year. Now apply that to a 40-year transit at 10% of light speed. The cumulative dose comes out to somewhere between 16 and 24 sieverts. Let that land. NASA's career radiation limit for astronauts is 600 millisieverts. That figure corresponds to a 3% increase in lifetime fatal cancer risk, which the agency considers the upper boundary of acceptable. A 40-year interstellar crossing, unshielded, would expose the crew to a dose that exceeds that career limit by a factor of 20 to 40. Not slightly over the limit, not twice the limit, 20 to 40 times. At 5 sieverts of acute exposure, roughly half of people die without aggressive medical treatment. At 20 sieverts of acute exposure, death follows within days. Even the chronic version of these doses, stretched across years rather than arriving all at once, elevates cancer risk by hundreds of percent above baseline. And the damage is not limited to the body. Studies of atomic bomb survivors and radiation workers showed that doses above 1 sievert raise rates of leukemia, solid tumors, cardiovascular disease, and cataracts. Doses of several sieverts produce measurable cognitive damage. The hippocampus and the prefrontal cortex, the brain regions most responsible for memory and decision-making, are particularly vulnerable. Research from Brookhaven National Laboratory, using heavy ion beams to simulate galactic cosmic rays in animals, found persistent neuroinflammation, accelerated brain aging, and lasting behavioral changes. No therapeutic remedy has been identified. The crew that lands at Proxima may not be the same people, cognitively or neurologically, who departed Earth. The reading came back reversed. The instinct is to solve this with shielding. Build thicker walls. Wrap the crew compartment in lead or steel. But galactic cosmic rays are so energetic that dense shielding actually makes things worse. When a high-energy particle hits a heavy nucleus in the shielding material, it fragments. The result is a spray of secondary particles, neutrons and pions, produced in a process called spallation. Think of it like this: armor designed to stop a single bullet instead shatters it into a hailstorm of smaller projectiles. The hailstorm can be more biologically damaging than the original round. The best shielding material for cosmic rays is hydrogen-rich. Water works. Polyethylene works. Both contain abundant hydrogen nuclei which absorb and scatter the incoming particles without the same spallation cascade. But to halve the cosmic ray dose, the crew compartment would need roughly 20 to 30 centimeters of water-equivalent shielding wrapped around the entire habitable volume. For a habitat comparable in size to the International Space Station, roughly 900 cubic meters, the shielding mass runs into the hundreds of tons. Every additional ton compounds the propulsion problem that everything else in this story has already made nearly unsolvable. Magnetic shielding has been proposed as an alternative, a superconducting coil system generating a magnetic field around the ship, mimicking what Earth's magnetosphere does for the planet. In principle, it could deflect charged particles without mass penalties. In practice, no prototype has ever been built. The field strengths required and the physical dimensions of the coil structures needed to produce them exceed anything current superconducting technology can deliver. The radiation problem has no clean solution, not a passive one, not an active one. Now set radiation aside for a moment and ask how the crew eats, drinks, and breathes. The International Space Station supports 6 or 7 people in low Earth orbit. It recycles some water and some oxygen. In 2023, a significant milestone was reached when the Environmental Control and Life Support System, the ECLSS, achieved approximately 98% water recovery with the addition of the brine processor assembly. Humidity, urine, wastewater, all of it processed and returned as drinking water. 98% recovery is remarkable. The remaining 2% is replenished from Earth. Oxygen is produced primarily through electrolysis, splitting water molecules into hydrogen and oxygen, with additional supply arriving on cargo missions. Carbon dioxide removal relies on regenerable molecular sieves, chemical filters that capture exhaled CO2. The system experiences repeated component failures. Replacement parts arrive on the 8 to 12 cargo missions the station receives every year. When something breaks critically, the crew can return to Earth in hours aboard a docked Soyuz capsule or Crew Dragon. Ground engineers provide near real-time support across a communication delay of roughly 1 second. An interstellar mission has none of that. No resupply, no replacement parts, no emergency return. And the communication delay does not stay at 1 second. It grows over the course of the transit, from minutes to hours to years. A question sent to Earth from the midpoint of a 40-year journey at 10% of light speed would take roughly 2 years to arrive. The response would take another 2 years to return. By the time advice came back, 4 years would be gone. The crisis would be resolved, or the crew would be dead. This means the life support system must achieve something no system has ever achieved: 100% closure, complete recycling of water, oxygen, and ideally food, with zero input from outside, sustained for decades. The closest attempt was Biosphere 2. In the early 1990s, a sealed structure was built in the Arizona desert. 3.14 acres of enclosed ecosystem, 8 crew members, every form of life needed to sustain them, contained within glass and steel on the surface of Earth, with full sunlight available above and the ability to abort at any moment. It failed to achieve closure. Oxygen levels dropped dangerously and required external supplementation. Carbon dioxide fluctuated in ways that were not predicted. Insect populations collapsed, pollination failed, food production fell below the required caloric intake, and the crew experienced significant caloric restriction. Interpersonal conflict emerged under the pressure. The experiment demonstrated, under conditions far easier than any interstellar mission could offer, that a fully closed ecosystem is not something humanity knows how to build. Food production at crude scale introduces another layer. The ISS has grown lettuce, radishes, and chili peppers in small growth chambers. Those experiments demonstrate something important. Plants can germinate and grow in microgravity. What they did not demonstrate is how to feed people. Estimates for crew-scale agriculture on a long-duration mission run to hundreds of square meters of growing area, and some projections exceed 1,000 square meters of continuous cultivation, with 0 crop failures tolerated. On Earth, a bad growing season raises grocery prices. On a starship, a bad growing season means the crew begins to starve. There is no importing from elsewhere. There is no elsewhere. And then there is medicine. On the ISS, the crew has a limited medical kit, near real-time telemed support from Earth, and an emergency return option that can have them in a hospital within hours. An interstellar mission offers none of that. A single physician, if the crew is fortunate enough to have one, would need to handle every medical event for dozens to hundreds of people across 40 or more years. Trauma, surgical emergencies, appendicitis, intestinal obstruction, cardiac events, stroke, dental emergencies, which can become life-threatening when untreated, kidney stones, fractures, burns, and layered beneath all of that, the slow accumulation of chronic disease across a multi-decade mission. Diabetes, hypertension, autoimmune conditions, and cancer, made far more likely by the radiation environment already described. Surgery in space carries its own specific horror. Blood does not pool in microgravity. It forms floating globules that drift. Fluids migrate unpredictably. Instruments must be physically restrained. The patient must be immobilized. Even with a rotational artificial gravity providing some approximation of a gravitational field, Coriolis effects, the slight deflecting force produced by rotation, can cause nausea and disorientation that complicate any delicate procedure. No human surgical procedure has ever been performed in space. Not once. Not a minor one. Not an emergency. Never. The operating infrastructure required for even basic surgical capability adds mass and complexity. Sterilization equipment, anesthesia, blood supply and transfusion capability, post-operative care, and all of it must remain functional for 40 years, maintained by whoever is still capable of maintaining it. Infectious disease closes the loop. In a sealed atmospheric environment, every pathogen stays inside the system. A novel respiratory infection could move through the entire crew within days. There is no quarantine that actually works when everyone shares the same recycled air. Antibiotic-resistant bacteria evolve readily in closed environments. Research from the ISS suggests that microgravity may enhance the virulence of certain bacteria while simultaneously suppressing aspects of human immune function. The inability to evacuate transforms every gap in the medical kit into something else entirely. A condition that would be treated routinely in any hospital on Earth becomes, in that sealed loop 40 light years from help, a potential death sentence. The propulsion problem is staggering. The energy costs are civilizational in scale. The institutional endurance required has no historical precedent. But the human body in transit introduces a category of problem that does not yield to clever engineering in the same way. Radiation accumulates whether the engineering is clever or not. Biological systems require closure that has never been achieved. Medicine without evacuation is medicine without a safety net for anyone. The human leg of the journey may not be easier than the propulsion. It may be harder, and the hardest parts of it may be the ones that cannot be solved by building a better engine. There is still the question of what happens to the mind across 40 years. That layer of the problem is still ahead. And it isn't only the bodies that have to last 40 years. The machines do. The minds do. And so does whatever community holds them together. Start with the machines. The longest continuously operating human spacecraft in history are the Voyager probes. Launched in 1977, they have been functioning in deep space for nearly 50 years. That is the record. That is the benchmark. And it sounds reassuring until you understand what the Voyagers actually are. They have no moving parts in their primary structure, no life support, no pumps, no valves, no atmospheric processes. They are powered by radioisotope thermoelectric generators. which produce electricity from the slow decay of plutonium with no combustion, no rotation, no mechanical action of any kind. They are, in engineering terms, extraordinarily simple objects. And even so, several of Voyager 1's instruments have already failed. The power output drops roughly 4 watts every year. By the mid-2030s, there may not be enough power left to run a single instrument. That is the record. 50 years. Simple design. And it is already failing at the edges. A crude interstellar vessel is not a Voyager probe. It is a city in a bottle. It needs pumps to circulate coolant, valves to regulate pressure, compressors to manage atmosphere, heat exchangers to shed waste energy, electrical distribution networks spanning the entire ship, computer systems running navigation and environmental control simultaneously, atmospheric processes scrubbing carbon dioxide from the air, water purification systems operating continuously, food production chambers sustaining the crew across decades, medical equipment that must function without resupply, communications arrays, structural monitoring sensors, and a propulsion system that must reignite perfectly after sitting dormant for decades at the far end of the journey. Each of those systems contains hundreds of components. Each component can fail. None of them have the Voyager's luxury of mechanical simplicity, and everything ages. Rubber seals crack under decades of thermal cycling. Bearings wear. Solder joints develop microfractures as the ship expands and contracts through temperature shifts. Circuit boards accumulate radiation damage gradually and silently. Lubricants either evaporate into the vacuum or polymerize into useless residue. On Earth, these are maintenance problems. There are supply chains, manufacturing facilities, trained technicians, and replacement parts. None of those exist on an interstellar ship. What exists is what was packed at departure. 3-dimensional printing is often proposed as the solution. Print what you need on board. But 3D printing, even at its current best, is limited to simple geometries in a narrow range of materials. It cannot print a high-precision bearing to flight tolerances. It cannot reproduce a complex circuit board. It cannot fabricate a high-pressure valve seal that will hold for the next 15 years. The precision required for critical components is the precision of a factory, not a workshop. The failure mode here is not dramatic. The ship does not explode. It degrades. The air scrubbers lose efficiency slowly and measurably, and then faster. The water recycler begins returning water that requires an extra pass to be safe, and then 2 passes, and eventually cannot keep up. The food production chambers fail one by one, as lighting arrays burn out and nutrient delivery systems clog. The ship doesn't become a fireball. It becomes progressively less habitable, and then uninhabitable, over a span of months or years, while everyone aboard watches the margins narrow. Then the data shifted. The psychological dimension of that slow degradation may be just as dangerous as the mechanical one. We have data, not from interstellar missions, but from the closest analogs available. Antarctic research stations, where small crews overwinter in near total isolation for months at a time. Submarine deployments, where crews operate in sealed vessels under sustained pressure. And the Mars 500 experiment, conducted between 2010 and 2011, which confined 6 volunteers in a sealed facility for 520 days to simulate the psychological effects of a Mars transit. The findings were not reassuring. Documented effects across all 3 environments include depression, anxiety, interpersonal conflict, disrupted sleep, cognitive decline, and motivational collapse. In the Mars 500 study specifically, researchers recorded increased sedentariness across the group, significant disruption of sleep-wake cycles, and measurable declines in alertness and cognitive performance. And that experiment had a known endpoint. Everyone inside that facility understood that the door would open in 520 days. The psychological relief provided by a fixed terminus is not a trivial variable. It is the difference between enduring something and enduring something without knowing whether it ends. An interstellar crew has no such assurance. As the mission extends, the communication delay grows. Early in the journey, messages from Earth arrive within hours. Later, within days. At the halfway point, a message takes years to arrive and another 2 years for any reply to come back. The people sending those replies will have changed. The events they describe will be years in the past. Relationships, institutions, everything familiar will have shifted in ways the crew cannot fully comprehend from a distance. The crew exists in a communicative void. They are watching ghostly echoes of a world that no longer quite matches the world they left. We have no data for human group dynamics across 10 to 40 years of sealed confinement. Not approximations, not extrapolations from shorter studies, no data. We are guessing. Now add the governance problem. Every community needs authority, mechanisms to make decisions, resolve conflict, allocate resources. On Earth, those mechanisms evolved over centuries, refined through trial and catastrophe. And on Earth, a person who cannot accept the authority structure can, in principle, leave. On a starship, no one can leave. A hierarchical model, structured like a military command, offers clarity, clear lines of authority, rapid decision-making, defined roles. But without external accountability, it risks becoming authoritarian. There is no appeal to a higher court. There is no election. There is no mechanism of removal that does not itself require whoever holds authority to enforce. A democratic model offers broader participation, but a sealed population of a few hundred people that cannot exit is vulnerable to factional gridlock and to majority tyranny with no escape valve for the minority. A hybrid model must define where technical authority ends and communal authority begins. On a starship, nearly every decision has life or death implications. The boundary between those two domains is contested by definition. And then there is succession. A 40-year mission outlasts any individual leader's career. Leadership will change hands. In human history, the most dangerous moment for any closed political system is the transition of power. Sailing ships mutinied. Isolated colonial outposts fragmented. Succession crises in closed political systems have destabilized and destroyed communities with resources and alternatives. On a starship, succession failure does not threaten governance. It threatens the air system, the water system, the people running them. This leads to the generation ship concept, which is sometimes presented as the solution to everything. Accept that no individual crew completes the journey. Build a self-sustaining community. Let the voyage span generations. Demographic modeling suggests minimum viable populations of several hundred to a few thousand, enough for genetic diversity and social structure over a century or more. But generation ships do not solve the problem. They relocate it. A larger population demands proportionally larger life support, food production, water recycling, medical infrastructure, and living space. The mass and complexity of a generation ship dwarf every serious engineering study conducted on interstellar mission design. That is one problem. The deeper problem is this: the founding crew chose the mission. Their children did not. The children born into that ship will grow up in a sealed vessel, crossing interstellar space, committed by their parents' decision to a destination they may never have wanted, unable to leave, unable to refuse. Whether it is morally permissible to create human beings whose entire existence is constrained by ancestral mission choices is a question philosophy has not resolved. It may not be resolvable. A generation ship is not just an engineering project. It is a question about the limits of one generation's authority over the next. In 2020, a small air leak was detected in the Zvezda module of the International Space Station. The hole in that section was more than 20 years old. Finding the source took months. The patch used onboard materials it held. In 2007, a computer failure in the Russian segment simultaneously disabled attitude control and oxygen generation. It took days of intensive engineering support from the ground to restore systems. In late 2013, an external coolant pump module failed during the holidays, requiring unplanned spacewalks to install a spare that had been delivered by a prior resupply mission. In each case, the resolution required something the interstellar mission cannot have: ground expertise available in near real time, Earth-supplied components, deferred resupply from a cargo vehicle already en route. Remove those 3 lifelines and every one of those incidents becomes something else entirely. Suspended animation is the escape from all of this in most science fiction. Put the crew to sleep. Wake them up at the destination. Bypass the psychology, the governance, the machinery degradation, the slow decades in the void. No human being has ever been placed in suspended animation and revived. That is not a caveat. It is the full state of the technology. Therapeutic hypothermia, lowering core body temperature by a few degrees, is used in medicine to slow metabolic activity during cardiac surgery or stroke treatment. The durations involved are hours to days, not months, not years. Some species, ground squirrels, bears, certain frogs, enter hibernation or torpor. Research into the underlying biology is ongoing and still preliminary. The unsolved problems include cellular damage from prolonged metabolic suppression, how the body would receive hydration and nutrition across years of reduced function, ice crystal formation in tissues at lower temperatures, and the severe muscle and bone atrophy that would accumulate across decades even in an active crew. Suspended animation for interstellar travel is a hope. It is not a plan. The human leg of this mission contains multiple unsolved problems. Mechanical reliability across timescales no engineered system has ever survived. Psychological endurance across durations no study has ever tested. Governance structures for communities that cannot exit and cannot appeal to outside authority. The ethics of generational commitment across people who never consented. And a speculative biology technology that does not exist. Any one of these could end the mission. The question is not which one is hardest. The question is whether all of them can be solved simultaneously by the same civilization, before anyone departs. That question does not yet have an answer, and the list of problems is not finished. Suppose every one of those problems is solved. Suppose mechanical reliability is achieved across 4 decades. Suppose psychology holds, governance holds, life support holds, and suspended animation proves out. Suppose the crew departs, survives the crossing, and approaches the Proxima system after 40 years in transit. There is still one more thing. The ship has to stop. This is where most discussions of interstellar travel quietly look away. Reaching the destination is not the same as arriving at the destination. At 10% of the speed of light, the Proxima system, including any planetary orbits, spans only a few astronomical units across. At that speed, without any deceleration, the entire system does not appear on the horizon and slowly grow. It flashes by in hours. The encounter with Proxima b, if it can be called that, lasts at most a few hours, possibly less. A flyby is a glimpse, not a mission. For a crew that left Earth when they were young adults, watched children grow up aboard the ship, buried the dead, rebuilt equipment, and endured 4 decades of silence and isolation in pursuit of a single goal, arriving too fast to stop is not a technical disappointment. It is a tragedy with no remedy. True arrival requires shedding nearly all of the kinetic energy the ship accumulated over years of acceleration. And this is where the physics becomes brutal in a new way. Acceleration was hard, but it benefited from everything in the solar system. Established infrastructure, ground-based power, launch pads, orbital assembly stations, the full industrial output of Earth. Deceleration happens in isolation, 4 light years from any of that, approaching a dim red star. Whatever the ship needs to slow down, it carries with it. The most straightforward approach is to carry deceleration fuel. The problem is the rocket equation. The mass ratios required to accelerate a crewed ship to 10% of light speed already push toward the outer edge of what fusion propulsion could theoretically manage. Braking at the destination demands roughly the same energy as accelerating in the first place. Applying the rocket equation to both legs of the journey, the required fuel-to-payload mass ratio does not merely double, it compounds. A ratio of roughly 10 for a flyby mission becomes a ratio of 100 or more for a full acceleration and deceleration profile. The ship that could theoretically make the crossing as a flyby vessel would need to be an order of magnitude more massive to stop at the end. There are alternatives. A magnetic sail uses a large superconducting loop to generate a magnetic field that interacts with charged particles in the interstellar medium and the stellar wind ahead of the destination. It is not propulsion in reverse. It is drag. Physically, the concept is valid. A field of sufficient size and strength would produce braking force against the diffuse stream of particles. But the force is small. The deceleration phase could last years. And the sail must be deployed and operated reliably after 40 years of cosmic ray exposure, vibration, thermal cycling, and storage in interstellar space. No magnetic sail of any kind has ever been built or tested. Not a prototype, not a scaled-down version, not a laboratory analog. The math exists. The hardware does not. Another option is photon pressure braking. Use the light from Proxima itself to push against a large reflective sail and slow the ship. This works elegantly for gram-scale light probes. For a crewed vessel, it fails for a simple reason. Proxima Centauri is a dim star. Its luminosity is only about 16 10,000ths of the sun's output. The photon pressure a crewed ship could extract from Proxima's light across a sail of any practical size is nowhere near sufficient to arrest tens of thousands of tons moving at a significant fraction of light speed. That is when the pattern broke. Even setting aside the question of how to slow down, the ship still has to survive the crossing. At 10% of light speed, the interstellar medium is not empty. The interstellar medium averages roughly 1 atom per cubic centimeter. Sparse. By everyday standards, a nearly perfect vacuum. But at that speed, even individual hydrogen atoms deliver a meaningful dose of radiation with each impact. Dust grains are far more dangerous. A single grain of dust with a mass of 1 microgram, struck at 10% of the speed of light, releases kinetic energy equivalent to a small explosive charge. The interstellar medium contains dust, not densely, but over 4¼ light years of continuous travel, the cumulative bombardment is significant. Every forward-facing surface of the ship is being sandblasted for decades. Sacrificial bumper shields can absorb some of the damage. Electromagnetic fields can deflect charged particles. Strategic orientation can protect the most vulnerable components. None of these approaches has been tested under anything resembling realistic interstellar conditions. And during deceleration, the ship reorients to fire its engines or deploy braking systems, changing the geometry of protection entirely. Surfaces that were shielded are now exposed. Surfaces that were exposed are now tucked away. The ship must survive both configurations across an unbroken 40-year voyage. And then comes the final test, the engine reignition. No rocket engine in human history has ever been required to restart after decades of inactivity and perform at full capacity on demand. Turbopumps, injectors, combustion chambers, fuel lines, and valve systems are precision instruments. In controlled laboratory environments, on the ground, with a regular inspection and maintenance, they degrade. In interstellar space, after 40 years of cosmic ray bombardment, thermal cycling, material fatigue, and zero maintenance access, expecting flawless reignition is not engineering optimism. It is optimism verging on faith. The failure modes are not recoverable. Partial deceleration failure means the ship enters the Proxima system too fast for orbital capture. It threads through the system and continues outward into deep space, unable to stop or turn around. Total deceleration failure means the same permanently. There is no second attempt. There is no rescue mission. There is no message that arrives in time to help. The round-trip communication delay at that distance is over 8 years. By the time Earth learns the engines failed, the ship is already gone. And suppose none of that happens. Suppose the deceleration works. The crew achieves orbit around Proxima b, and they look out the windows at the planet they have spent 4 decades traveling to reach. Here is the last reveal that the original announcement in August 2016 did not include. We do not know what Proxima b actually is. Habitable zone is a definition, not a guarantee. The zone describes where liquid water could exist on a planet's surface under the right conditions. It says nothing about whether those conditions exist. Proxima Centauri is an active flare star. It emits bursts of ultraviolet radiation and X-rays that can strip unprotected planetary atmospheres over geological time, molecule by molecule. Whether Proxima b retains any atmosphere at all depends on factors we have not measured. The strength of the planet's magnetic field, the original thickness of its atmosphere, the precise history of stellar activity across billions of years. The planet is likely tidally locked, one hemisphere in permanent daylight, one in permanent night, though a Mercury-style spin-orbit resonance is possible if the orbit carries even modest eccentricity. Surface conditions vary dramatically between those two possibilities. Whether atmospheric circulation could distribute heat across the terminator line and produce habitable conditions is still an open modeling question, with no consensus answer. Proxima b might be a living world with oceans and weather. It might be a desiccated rock, scoured bare by radiation over billions of years. It might sustain a narrow band of partially habitable conditions in the twilight zone between its hemispheres. The crew that arrives after 40 years finds out only at that moment. After every resource is spent, after every bridge is burned, after the only ship that could take them home has been committed to the mission. Now draw back and look at the full picture. The mission requires orbital assembly infrastructure that does not yet exist, propulsion systems that have not been invented, energy budgets that exceed the output of entire civilizations, life support closure that has never been demonstrated for more than brief experimental durations, radiation shielding solutions that have not been proven for crude interstellar transit, mechanical reliability across timescales no engineered system has ever approached, psychological endurance across durations no study has measured, deceleration after decades of dormancy performed by engines no propulsion system has ever been asked to replicate, and a destination whose actual character remains unknown. Physics permits all of it. Engineering has not achieved any of it. There is a useful distinction in the philosophy of technology between theoretical possibility and practical accessibility. Counting every grain of sand on Earth is theoretically possible. Building a tower from the surface to geostationary orbit is theoretically possible. Disassembling Mercury to construct a shell around the Sun is theoretically possible. None of them is practically accessible to any civilization that has ever existed or that exists today. Theoretical permission and practical achievement are separated by something real, something that takes work to close, and something that does not close on its own. Consider walking from New York to Beijing. The path exists. The body is capable of walking. The ocean makes it effectively impossible for any individual standing on shore. The nearest star is humanity's ocean. We have not returned humans to the lunar surface since 1972. Artemis, the program designed to do so, has faced delays accumulating across more than a decade. We have never sent a crewed mission beyond the Earth-Moon system. We have never demonstrated closed-loop life support beyond short experimental durations. We have never operated a fusion reactor that produces sustained net energy. We have never built a spacecraft capable of even 1% of light speed. We have never tested any form of interstellar propulsion beyond small-scale laboratory demonstrations and computer simulations. The gap between where we stand and what the mission requires is not a crack, it is a canyon. The terrifying part is not that the stars are far. Distance alone would be a problem of patience. The terrifying part is that the nearest star, the one with a name and a planet we have already detected, may sit beyond practical human reach. Not because physics forbids the crossing. Physics does not forbid it. But because the crossing demands more than we have built, more than we can currently build, and more than we will be able to build for a very long time. This is a statement of scale, not hopelessness. Somewhere tonight, under the right conditions, someone standing in the southern sky can find the constellation Centaurus. In that direction, invisible to the naked eye, a faint red star is there. It has a planet. The planet is in the habitable zone. It is the closest world orbiting any star other than our own. And it is, by every honest accounting of what we know and what we can do, beyond practical reach. Scale is not a sentence. It is a description of where we are now. Ambition has moved before against distances that looked impossible. Powered flight to the moon happened in a single century. Thousands of exoplanets, the image of a black hole's shadow, the detection of gravitational waves rippling through space-time, all arrived within a single generation of science. The gap between Apollo's lunar distance, measured in 1.3 light seconds, and Proxima Centauri, measured in 4.24 light years, is a factor of roughly 100 million. Crossing it will require a civilizational transformation. New physics translated into new engineering. New engineering sustained across a new timescales. New commitment maintained across generations who have not yet been born. That transformation has not happened yet. It may happen. The universe does not prohibit it. But the universe does not wait for it either. Out there in Centaurus, the red star continues to burn. its planet continues to orbit, and the distance between here and there remains exactly what it is. Scale, in the end, is what the universe does best,